There's something quietly extraordinary happening inside our nearest galactic neighbour, something we've only just begun to understand. For decades we thought we knew Andromeda, that magnificent spiral of stars slowly drifting toward us across 2.5 million light-years of space. But recent observations have revealed something unexpected at its heart, something that changes how we see not just Andromeda, but the very nature of galactic evolution itself. Tonight, we'll explore this discovery step by step, using real astronomical data, the patient work of radio telescopes, and the gentle unfolding of cosmic mysteries that have been waiting billions of years to be noticed. It's a story of hidden structures, ancient collisions, and the quiet drama playing out in what we once thought was empty space. If this calm journey through deep space helps you drift toward rest or wonder, your gentle like, your soft subscribe, and your thoughtful comments create a community I treasure. Now, let's begin this exploration together, moving gently into the heart of our galactic neighbour. Have you ever wondered what secrets hide in the faint smudge of light visible on clear autumn nights, that distant beacon we call the Andromeda Galaxy? Tonight we embark on a gentle journey across 2.5 million light-years of space, moving at our own comfortable pace through one of astronomy's most revolutionary discoveries. Whether you're settling into bed, taking an evening walk, or simply finding a quiet moment to explore the cosmos, this investigation will unfold slowly, like starlight itself crossing the vast emptiness between worlds. If this peaceful exploration brings you knowledge or comfort, your soft subscription and thoughtful engagement help create a community of cosmic wanderers I deeply treasure. There's absolutely no need to rush through this mystery, no pressure to grasp everything immediately, because the most profound truths in astronomy reveal themselves through patient observation and gentle contemplation. What makes Andromeda so remarkable isn't just its status as our nearest major galactic neighbour, but how it serves as a cosmic mirror, reflecting back truths about galaxy formation that we simply cannot observe from within our own Milky Way. Think of trying to understand the architecture of your hometown while standing in its very centre, surrounded by buildings and streets that block your view of the larger pattern. This is precisely our predicament when studying the Milky Way from Earth, embedded as we are within its spiral arms, dust lanes, and stellar populations. Andromeda offers us something invaluable, an external perspective on spiral galaxy structure and evolution, a celestial laboratory where we can observe processes that remain hidden within our own galactic home. On exceptionally dark nights, away from city lights, Andromeda appears as a fuzzy, elongated patch roughly 6 times wider than the full moon, though much fainter, requiring your eyes to adjust fully to darkness before it becomes visible to the naked eye. This pale glow carries profound significance beyond its modest appearance, representing the accumulated light of approximately 1 trillion stars, each potentially hosting planetary systems, stellar nurseries, and cosmic phenomena we're only beginning to understand. The photons reaching your retina tonight began their journey when early human ancestors first walked upright on African savannas, travelling through the cosmic void for over 2 million years before finally arriving at Earth. When we observe Andromeda, we're not just seeing a distant collection of stars, but witnessing a galactic time capsule, a preserved moment from Earth's ancient past when our planet's continents held different shapes and life itself followed dramatically different evolutionary paths. This year marks a particularly meaningful milestone in our relationship with this cosmic neighbour, as 2025 celebrates exactly 1 century since Edwin Hubble's groundbreaking announcement that fundamentally transformed our understanding of the universe itself. In January 2025, Hubble revealed that Andromeda was not a nearby gas cloud within our own galaxy, as previously believed, but an entirely separate stellar island floating in the cosmic ocean, comparable in size and complexity to our own Milky Way. Overnight, this single discovery expanded the known universe from 1 galaxy to billions, from a cosmos measured in thousands of light years to one spanning billions, from a relatively cozy celestial neighbourhood to an almost incomprehensibly vast expanse filled with countless galactic cities. The implications rippled through every aspect of astronomy and philosophy, forcing humanity to confront its true position in a universe far grander and more mysterious than anyone had dared imagine. Yet even Hubble himself could never have predicted what modern technology would eventually reveal about this distant galaxy, discoveries that challenge our most fundamental assumptions about cosmic evolution, dark matter, and the very nature of galactic formation processes that shape our universe. What transforms a seemingly ordinary autumn evening into a portal connecting you directly with cosmic history spanning millions of years? Standing beneath a truly dark sky, away from the glowing interference of streetlights and urban illumination, your eyes gradually adapt to reveal celestial treasures in visible moments before. Among these emerging stellar jewels, one particular smudge of light holds extraordinary significance. A faint, elongated glow positioned just northeast of the distinctive square pattern astronomers call Pegasus. This ghostly luminescence represents Andromeda, appearing deceptively modest despite harbouring secrets that revolutionize our comprehension of galactic evolution. The experience resembles spotting a neighbour's house across a vast valley at twilight, recognizing its familiar silhouette while remaining completely unaware of the complex lives, stories, and activities unfolding within those distant walls. Andromeda presents this same tantalizing combination of recognition and mystery, visible enough to locate with patience and proper conditions, yet concealing incredible complexity beneath its understated appearance. Your naked eye perception captures only the galaxy's brilliant central bulge, where ancient yellow stars cluster in gravitational embrace, while the magnificent spiral arms extending far beyond remain invisible without telescopic assistance. This limitation creates a fascinating paradox. Andromeda actually spans an angular width approximately 6 times greater than our full moon, meaning if human vision could detect its complete structure, this galactic neighbour would dominate autumn skies with breathtaking prominence. Instead, atmospheric scattering, light pollution, and the limitations of human retinal sensitivity combine to reveal merely the galaxy's brightest core, leaving vast stellar territories hidden in apparent emptiness. The faint photons reaching Earth tonight carry information encoded during humanity's earliest evolutionary chapters, when Australopithecus species roamed African landscapes and ice ages, periodically transformed continental climates. These ancient messengers of light departed Andromeda's stellar cities approximately 2.5 million years ago, beginning an uninterrupted journey across intergalactic space at precisely 86,000 miles per second. Throughout their cosmic voyage, these photons witnessed the birth and death of countless stars, navigated through gravitational fields that bent space-time itself, and somehow avoided absorption by the interstellar dust clouds that could have terminated their mission before completion. The temporal disconnect becomes even more profound when considering that modern telescope observations reveal Andromeda as it appeared when Earth's magnetic field underwent dramatic reversals, when entirely different animal species populated our planet's ecosystems, and when the Himalayas stood considerably lower than today's towering peaks. This ancient light carries within its wavelengths detailed information about stellar populations, chemical compositions, and galactic structures that existed during epochs when human consciousness remained millions of years in the future. Every autumn evening offers renewed opportunity to witness this cosmic time machine. Though atmospheric conditions, lunar phases, and seasonal weather patterns significantly influence visibility success, the optimal viewing window occurs during moonless nights in October and November, when Andromeda climbs highest above the horizon and atmospheric turbulence typically reaches seasonal minimums. Urban astronomers face additional challenges from sky glow, that orange dome of artificial illumination that washes out faint celestial objects and forces dedicated stargazers to travel considerable distances seeking truly dark observing sites. Rural locations, mountain observatories, and designated dark sky preserves offer dramatically improved viewing conditions, where Andromeda transforms from barely perceptible smudge into clearly defined oval structure extending across multiple degrees of sky. Even under perfect conditions, detecting this galactic neighbour requires patience, allowing your eyes adequate time for complete dark adaptation while resisting the temptation to use flashlights or check mobile phone screens. The human visual system requires approximately 30 minutes to achieve maximum sensitivity, during which specialized retinal cells called rods accumulate the photosensitive chemicals necessary for detecting extremely faint light sources. Once achieved, this enhanced night vision reveals not only Andromeda but numerous other deep sky treasures previously invisible, transforming familiar constellation patterns into richly detailed cosmic landscapes populated with star clusters, nebulae, and distant galaxies. The philosophical implications of this simple observation experience extend far beyond astronomy, connecting modern observers with countless previous generations who gazed upward, seeking understanding, meaning, and perspective within the vast cosmic arena surrounding our tiny planetary home. How does a single scientific announcement completely shatter humanity's conception of cosmic scale and our place within the universe? January 1925 witnessed one of astronomy's most revolutionary moments when Edwin Hubble stepped before colleagues at the American Astronomical Society meeting to present findings that would fundamentally rewrite our understanding of reality itself. For centuries, astronomers had catalogued mysterious spiral-shaped clouds scattered across the heavens, classifying these ethereal formations as nebulae within our own Milky Way system. These ghostly spirals sparked intense debate among scientific communities, with some researchers proposing they might represent distant stellar systems while others maintained they were merely local gas clouds illuminated by nearby starlight. Hubble's methodical observations using Mount Wilson Observatory's powerful telescope resolved this cosmic controversy through precise measurements of individual variable stars within Andromeda's apparent boundaries. These special stars, called Cepheid variables, pulsate with predictable rhythms directly related to their intrinsic brightness, providing astronomers with reliable cosmic distance indicators. By comparing these stars' apparent faintness with their calculated luminosity, Hubble determined that Andromeda lay far beyond any conceivable boundary of our galactic home. The mathematical calculations yield a staggering distance measurement, approximately 900,000 light-years, later refined to today's accepted value of 2.5 million light-years. This revelation transformed Andromeda from a nearby curiosity into a completely separate galactic entity, comparable in scope and stellar population to our entire Milky Way system. Overnight, the known universe expanded from a single galactic island to an ocean containing countless similar stellar cities, each harboring billions of suns and potentially countless worlds. The philosophical ramifications cascaded through every aspect of human thought, forcing our species to confront its true cosmic insignificance while simultaneously revealing the magnificent scale of creation surrounding us. Previously, Earth occupied center stage within a cosmic theatre measured in mere thousands of light-years, where humanity could imagine itself holding special significance within creation's grand design. Hubble's discovery relegated our planet to an infinitesimal speck orbiting an ordinary star within one galaxy among billions, fundamentally altering perspectives on life, meaning, and humanity's role in the cosmic story. Religious leaders grappled with theological implications, while philosophers wrestled with questions of purpose and significance within such vast expanses. Scientists recognized that their understanding of stellar evolution, cosmic chemistry, and universal structure required complete revision to accommodate this expanded reality. The announcement marked the beginning of modern cosmology, establishing foundations for discoveries about universal expansion, galactic evolution, and the ultimate fate of everything we observe. Hubble's work demonstrated that spiral nebulae represented independent stellar systems comparable to our own Milky Way, suggesting that galaxy formation processes operated on scales previously unimaginable. This insight opened entirely new research fields investigating how galaxies form, evolve, interact, and distribute themselves throughout cosmic space. The century following Hubble's announcement witnessed unprecedented advances in astronomical technology, from radio telescopes detecting invisible radiation to space-based observatories operating beyond atmospheric interference. Each technological breakthrough revealed additional layers of complexity within galactic systems, exposing phenomena like supermassive black holes, dark matter halos, stellar nurseries, and exotic physical processes operating under extreme conditions. Modern astronomers now recognize that our local group contains over 50 galaxies bound together by gravitational attraction, with Andromeda serving as the dominant member whose future collision with our Milky Way will reshape both systems approximately 4 billion years hence. Yet even as we celebrate this centennial milestone of Hubble's groundbreaking discovery, new observations continue challenging fundamental assumptions about galactic structure, evolution, and the mysterious substances governing cosmic architecture. Today's most sophisticated instruments reveal Andromeda harboring secrets that would astonish even Hubble himself, discoveries that once again force us to reconsider everything we thought we understood about galaxy formation and cosmic evolution. The parallel between 1925 and 2025 becomes strikingly apparent as contemporary astronomers announce findings about Andromeda's composition, history, structure that may prove equally revolutionary to our cosmic worldview. Where Hubble revealed the existence of external galaxies, modern research uncovers fundamental mysteries about dark matter distribution, galactic merger history, and the processes shaping large-scale cosmic architecture that continue reshaping our understanding of universal principles, governing everything from stellar birth to galactic death. What fundamental challenges do astronomers face when trying to understand the very galaxy that serves as their observational platform? Imagine attempting to comprehend Manhattan's complete architectural layout, traffic patterns, and urban development while standing permanently fixed within Central Park, unable to move beyond the surrounding buildings that block your comprehensive view. This precise predicament confronts every astronomer studying our Milky Way's structure, composition, and evolutionary history from our embedded position within its spiral arms. Earth orbits a single star among hundreds of billions, positioned roughly 26,000 light-years from the galactic center, surrounded by dust clouds that obscure distant regions and stellar populations that remain forever hidden behind intervening cosmic debris. Our perspective resembles that of a microorganism living within a vast forest, attempting to map the woodland's complete ecosystem without ever glimpsing the canopy above or boundaries beyond the immediate tree trunks. Andromeda transforms this observational limitation into extraordinary opportunity, providing astronomers with an external laboratory where spiral galaxy physics unfolds in complete detail. Unlike our restricted internal viewpoint of the Milky Way, Andromeda presents itself tilted at precisely 7 degrees relative to Earth's line of sight, offering an oblique perspective that reveals both face-on spiral structure and edge-on stellar distribution simultaneously. This fortuitous orientation allows detailed study of phenomena impossible to investigate within our own galactic system. How spiral arms maintain their distinctive patterns across billions of years, where star formation processes concentrate within galactic disks, how stellar populations stratify by age and chemical composition, and what mechanisms drive the complex interactions between gas, dust, and magnetic fields that govern galactic evolution. The scientific proxy relationship between Andromeda and typical spiral galaxies extends far beyond mere convenience, representing one of astronomy's most productive research strategies. When astronomers develop theories about spiral galaxy formation, stellar evolution within galactic environments, or the distribution of dark matter around massive stellar systems, Andromeda provides the testing ground where predictions meet observational reality. Every measurement of Andromeda's stellar populations, chemical gradients, rotational velocities, and structural components contributes data points applicable to understanding thousands of similar systems scattered throughout the observable universe. This galactic laboratory approach has revealed fundamental principles governing how spiral galaxies assemble their mass, regulate star formation rates, interact with surrounding dark matter halos, and respond to gravitational perturbations from neighbouring systems. Andromeda's proximity enables astronomers to resolve individual stars within its spiral arms, something impossible for more distant galaxies where entire stellar associations appear as single points of light. This resolution advantage permits detailed studies of stellar evolution, planetary nebula formation, supernova explosions, and variable star behaviour within galactic context dramatically, different from solar neighbourhood conditions. Modern telescopic technology can distinguish red giant stars, massive blue supergiants, and even some white dwarf remnants scattered throughout Andromeda's disk and halo regions. Such observations provide crucial calibrations for understanding how stellar evolution proceeds within environments possessing different metallicity levels, star formation histories, and dynamical conditions than those characterizing our local galactic vicinity. The research implications extend into cosmology itself, as Andromeda serves as the nearest example of how galaxy formation processes operate within cosmic structures. Theoretical models predicting how primordial hydrogen and helium coalesced into stellar systems, how heavy elements dispersed throughout galactic volumes, and how supermassive black holes influence surrounding stellar populations all require observational verification through detailed studies of real galactic systems. Andromeda provides this verification opportunity at unprecedented resolution, allowing astronomers to test cosmological theories against actual measurements of stellar ages, chemical abundances, spatial distributions, and kinematic properties within a fully formed spiral galaxy. The scientific treasure trove extends beyond stellar astronomy into studies of interstellar medium physics, magnetic field configurations, cosmic ray propagation, and the intricate feedback mechanisms linking stellar death events with future star formation episodes. These processes operate throughout all spiral galaxies, but remain accessible for detailed investigation only within our immediate galactic neighbourhood and Andromeda itself. Current technological advances promise even greater revelations about spiral galaxy physics through Andromeda observations, as next-generation instruments achieve unprecedented sensitivity for detecting faint stellar populations, measuring precise radial velocities across galactic disks, and mapping the distribution of gas, dust, and dark matter components that determine galactic structure and evolution patterns governing the formation of cosmic architecture throughout the universe. Can the human mind truly grasp the staggering numerical reality of 1 trillion individual suns burning within a single galactic system? Andromeda's stellar census presents numbers that challenge comprehension, where each point of light represents a complete solar system potentially harbouring planets, moons, and perhaps even life forms developing under alien skies. To appreciate this scale, consider that counting these stars at 1 per second would require over 31,000 years of continuous effort, working without pause through day and night across centuries of human civilization. Yet even this temporal comparison fails to convey the true magnificence of Andromeda's stellar population, where ancient red giants slowly exhaust their nuclear fuel, while newborn blue supergiants blaze with temperatures exceeding 30,000 degrees, creating a cosmic ecosystem spanning every stage of stellar evolution simultaneously. The technological marvel of Hubble Space Telescope enables astronomers to resolve approximately 200 million individual stellar sources within Andromeda's sprawling architecture, though this represents merely the brightest tip of an enormous stellar iceberg. These detectable stars must exceed our own sun's luminosity to register as distinct objects across the 2.5 million light-year gulf separating our galactic neighbourhoods. Countless dimmer stars, including the red dwarf systems that comprise the majority of galactic stellar populations throughout the universe, remain forever invisible to current observational capabilities despite their overwhelming numerical dominance within Andromeda's total inventory. The relationship between visible and total stellar populations resembles examining a vast beach where only the largest pebbles catch your attention, while countless grains of sand escape notice despite forming the foundation supporting everything else. Each resolved star that Hubble captures in its detailed imaging campaigns represents a complete world system, possibly surrounded by rocky planets experiencing seasons, weather, patterns, and geological processes that mirror or exceed the complexity found within our own solar system. Some of these distant suns likely possess habitable zones where liquid water could exist on planetary surfaces, creating conditions suitable for biochemical processes that might lead to the emergence of consciousness, capable of gazing back across intergalactic space toward our own Milky Way. The observational challenge becomes even more remarkable when considering the precision required to distinguish individual stellar sources at such enormous distances. Andromeda's separation from Earth spans roughly 25 complete Milky Way diameters, a distance so vast that our entire galactic home could fit between Earth and our neighbouring galaxy system 25 times, with room remaining for additional cosmic real estate. This separation means that detailed study of Andromeda's stellar content requires optical resolution equivalent to spotting a flickering candle flame from a distance exceeding 60,000 miles, demanding technological sophistication that pushes the absolute limits of current engineering capabilities. Hubble's achievement in resolving individual stars across this cosmic gulf represents one of astronomy's greatest technical accomplishments, requiring orbital stability measured in milliseconds and optical precision that eliminates even the slightest vibration or thermal distortion that could blur these incredibly faint stellar signatures. The photons captured by Hubble's sensitive detectors carry detailed information about stellar surface temperatures, chemical compositions, evolutionary stages, and orbital motions that reveal the gravitational architecture governing Andromeda's internal structure. Advanced spectroscopic analysis of these stellar sources enables astronomers to determine which stars formed during different epochs of galactic history, how heavy elements produced by ancient supernovae dispersed throughout the galactic volume, and what dynamical processes shape the distribution patterns visible in contemporary observations. The grain of sand analogy extends beyond mere numerical comparison to encompass the fundamental physics governing stellar behavior within galactic environments. Just as each sand grain on a terrestrial beach possesses unique mineral composition, crystalline structure, and weathering history, every star within Andromeda carries distinctive signatures reflecting its birth environment, nuclear evolution pathway, and interaction history with surrounding stellar and interstellar components. Hubble's surveys reveal this stellar diversity in exquisite detail, showing how massive stars cluster within active star formation regions while lower mass systems populate the quieter halo regions surrounding Andromeda's main disk structure. The continuing investigation of Andromeda's stellar populations drives technological innovation in astronomical instrumentation, as future telescopes will push detection limits toward even fainter stellar sources, while achieving spectroscopic precision sufficient to measure individual stellar velocities, chemical abundances, and age determinations across the complete galactic system. These advancing capabilities promise revolutionary insights into galaxy formation processor, stellar evolution physics, and the cosmic chemical enrichment cycles that transformed primordial hydrogen into the complex atomic inventory supporting planetary formation and biological complexity throughout the universe. How does the Space Telescope become both artist and archaeologist, creating the most detailed portrait ever attempted of a neighbouring galactic civilization through years of methodical observation? Between 2010 and 2025, Hubble's Space Telescope embarked upon perhaps its most ambitious cartographic expedition, systematically photographing Andromeda's vast stellar territories with unprecedented precision and patience. This monumental undertaking required more than a decade of careful planning, orbital course scheduling and data collection, as Hubble methodically captured over 600 overlapping photographic fields across Andromeda's sprawling disk structure. Each individual exposure demanded precise pointing accuracy measured in thousandths of an arc-second, ensuring that stellar positions remained stable throughout lengthy integration times necessary to detect the faintest possible sources. The technical complexity resembled attempting to photograph every building, street, and landmark across an entire continent, while flying in a commercial aircraft, maintaining perfect focus despite atmospheric turbulence, mechanical vibrations, and constantly changing viewing angles. Hubble's orbital mechanics presented additional complications as the telescope circled Earth every 90 minutes, limiting observing windows when Andromeda occupied optimal positions within the instrument's field of view, while avoiding interference from sunlight, earthshine, and other bright celestial sources that could contaminate sensitive detector readings. The photographic mosaic gradually assembled through thousands of individual observations represents a masterpiece of both technological achievement and scientific dedication, requiring sophisticated computer algorithms to align, calibrate, and seamlessly blend separate images into a coherent, whole-spanning 2.5 billion pixels of digital information. This pixel density exceeds the resolution of typical high-definition television displays by factors of thousands, creating a digital canvas capable of preserving stellar details invisible to ground-based telescopes and revealing structural features that remained hidden throughout previous centuries of astronomical investigation. The data processing challenges alone demanded years of computational effort as astronomers developed specialized software tools for handling such enormous datasets while correcting for instrumental effects, cosmic ray impacts, background contamination, and the subtle geometric distortions introduced by Hubble's optical system. Each puzzle piece contributed unique information about stellar populations, dust lane structures, star formation regions, and the complex interplay between different galactic components that determine Andromeda's overall appearance and evolutionary trajectory. The overlapping photographic strategy ensured complete coverage across Andromeda's visible extent, while providing redundant measurements that improve statistical accuracy and enable detection of subtle variations in stellar density, color distribution, and morphological features that might escape notice in single exposures. Advanced imaging techniques captured multiple wavelengths simultaneously, allowing astronomers to distinguish between stellar types based on their spectral characteristics and construct detailed maps showing how different stellar populations distribute themselves throughout Andromeda's galactic architecture. The resulting mosaic reveals intricate spiral arm patterns, stellar associations, giant molecular cloud complexes, and the hierarchical clustering patterns that reflect gravitational processes operating across scales from individual stellar systems to the galaxy-spanning dark matter halo that governs Andromeda's large-scale structure. Years of patient accumulation transformed individual photographic snapshots into a comprehensive survey documenting stellar evolution, galactic chemistry, and the fossil records preserved within Andromeda's diverse stellar populations. This systematic approach enabled discovery of previously unknown stellar streams, shell structures, and other morphological features that provide crucial clues about Andromeda's merger history and the gravitational interactions that shaped its current configuration over billions of years of cosmic evolution. The photographic expedition also established new standards for astronomical survey methodology, demonstrating how space-based telescopes can achieve scientific objectives impossible from ground-based facilities despite atmospheric limitations, weather constraints, and the constant interference from terrestrial light pollution that compromises traditional observational strategies. Hubble's marathon documentation of Andromeda created an invaluable scientific archive that will support research investigations for decades to come, providing baseline measurements against which future observations can detect stellar motion, evolutionary changes, and the subtle transformations occurring within galactic systems over human timescales. The complete mosaic stands as testament to the power of sustained scientific effort, technological innovation, and international cooperation in pursuing knowledge that expands our understanding of cosmic processes governing galaxy formation, stellar evolution, and the fundamental physics operating throughout the universe. This decade-long commitment to systematic observation exemplifies how modern astronomy achieves its greatest discoveries through patience, precision, and the cumulative power of many individual measurements combining to reveal phenomena far beyond the scope of any single observation or brief investigative program. What secrets lie concealed beneath the graceful spiral patterns and glittering star formation regions that first captivate observers studying Andromeda's magnificent architecture? Initial examination of Hubble's comprehensive photographic survey reveals exactly what astronomers expected to find within a mature spiral galaxy. Sweeping arms traced by brilliant blue star clusters, reddish emission nebulae marking active stellar nurseries, and the familiar structural components that characterize disk galaxies throughout the cosmos. These surface features conform beautifully to established models of spiral galaxy evolution, displaying the characteristic density wave patterns that compress interstellar gas into new stellar generations while organizing galactic matter into the elegant geometric arrangements visible across billions of light-years. Massive star formation complexes shine with the distinctive blue-white radiance of young, hot stellar systems, while older populations contribute the warmer yellow and red hues associated with evolved giant stars nearing the end of their nuclear burning phases. Dust lanes weave intricate patterns between stellar associations, creating the complex interplay of light and shadow that gives spiral galaxies their distinctive visual appeal and provides the raw material for future episodes of star formation. These immediately apparent characteristics suggested that Andromeda represented a relatively straightforward example of spiral galaxy physics, following predictable evolutionary pathways that align with theoretical expectations derived from decades of galactic research and computational modelling efforts. However, astronomical investigation rarely ends with superficial observation, as the most profound discoveries often emerge through detailed analysis of phenomena invisible to direct examination. Advanced computational techniques applied to Hubble's unprecedented dataset began revealing subtle anomalies, unexpected distributions, and structural features that defied conventional interpretation within standard galactic evolution frameworks. Computer algorithms capable of analyzing stellar position data, color measurements, and brightness variations across millions of individual sources started detecting patterns that human observers could never recognize through visual inspection alone. These automated analysis systems identified stellar streams stretching far beyond Andromeda's main disk, unusual metallicity gradients within galactic halo regions, and kinematic signatures suggesting violent disruption events that occurred billions of years ago but left permanent imprints within contemporary stellar distributions. Sophisticated photometric techniques revealed that many stellar populations possessed chemical compositions and age characteristics incompatible with smooth, continuous galactic evolution models that astronomers had previously accepted as adequate explanations for spiral galaxy development processes. Statistical analysis of stellar velocities, spatial clustering patterns, and spectroscopic properties indicated that Andromeda's peaceful appearance masked a tumultuous history involving major gravitational disruptions, massive merger events, and dynamical processes far more complex than surface observations initially suggested. As astronomers began measuring the invisible components governing galactic structure and evolution, an entirely different picture of Andromeda's nature started emerging from the accumulated observational evidence. Dark matter's distribution patterns inferred from stellar orbital velocities showed unexpected deviations from theoretical predictions based on cosmological simulations of galaxy formation within cold dark matter frameworks. Gravitational modelling of stellar motions revealed mass concentrations and velocity dispersions that challenged fundamental assumptions about how spiral galaxies assemble their constituent matter and maintain structural stability over cosmic timescales. The invisible dark matter halo surrounding Andromeda appeared to possess properties significantly different from those predicted by standard cosmological models, suggesting either incomplete understanding of dark matter physics or the operation of galactic evolution processes not incorporated within current theoretical frameworks. Spectroscopic surveys measuring stellar radial velocities across different galactic regions detected kinematic signatures indicating that Andromeda's stellar disk had experienced significant heating episodes that disrupted the originally thin, rotationally supported configuration expected for undisturbed spiral systems. These observations pointed toward major merger events, capable of injecting massive amounts of orbital energy into galactic stellar populations, transforming their dynamical properties in ways that persist for billions of years after the initial gravitational encounters concluded. The emerging picture revealed Andromeda not as a pristine example of steady galactic evolution, but as a system bearing the scars of violent interactions that fundamentally altered its structure, composition, and evolutionary trajectory. This realization forced astronomers to reconsider basic assumptions about galaxy formation processes and the relative importance of mergers versus continuous accretion in determining the final properties of mature galactic systems throughout the universe. How did observations of spinning galaxies lead astronomers to conclude that most of the universe consists of completely invisible matter, whose nature remains one of science's greatest unsolved puzzles? During the 1970s, astronomer Vera Rubin conducted groundbreaking measurements of galactic rotation curves, studying how quickly stars orbit around galactic centers at various distances from these massive gravitational anchors. Classical physics predicted that stellar orbital velocities should decrease with increasing distance from galactic cores, following the same mathematical relationship that governs planetary motion within our solar system, where Mercury races around the Sun much faster than distant Neptune. However, Rubin's precise spectroscopic measurements revealed something extraordinary. Stars in the outer regions of spiral galaxies maintained surprisingly high orbital speeds, rotating far too quickly to remain gravitationally bound if galaxies contained only the visible matter that telescopes could directly detect through electromagnetic radiation. According to Newton's laws of gravitation, these rapidly moving outer stars should have been flung into intergalactic space billions of years ago. Yet spiral galaxies clearly maintain their structural integrity across cosmic timescales that span the entire history of the universe since galaxy formation began. This fundamental contradiction between theoretical predictions and observational reality forced astronomers to confront two possible explanations. Either gravitational physics operates differently on galactic scales than previously understood, or galaxies contain vast quantities of invisible matter whose gravitational influence prevents stellar populations from dispersing into the cosmic void. The dark matter hypothesis emerged as the preferred solution, proposing that every galaxy sits embedded within a massive halo of exotic particles that interact gravitationally with ordinary matter, but remain completely transparent to electromagnetic radiation, making them undetectable through conventional astronomical observation techniques. Andromeda played a crucial role in establishing the dark matter paradigm, providing the nearest large spiral galaxy where rotation curve measurements could achieve sufficient precision and to definitively confirm the presence of these mysterious gravitational influences. Detailed spectroscopic studies of Andromeda's stellar populations revealed the characteristic flat rotation curve signature that indicates dark matter dominance throughout galactic halos, with dark matter contributing approximately 5 times more mass than all the visible stars, gas and dust combined within typical spiral galaxy systems. This ratio suggested that ordinary atomic matter represents merely the visible tip of a much larger cosmic iceberg, with the bulk of galactic mass existing in forms completely unknown to terrestrial physics, despite decades of intensive experimental searches for dark matter particle candidates. The implications extended far beyond individual galaxies, as cosmological models incorporating dark matter successfully explained the formation of large-scale cosmic structure, the patterns observed in the cosmic microwave background radiation, and the evolution of galaxy clusters throughout the history of the universe. Andromeda's dark matter halo was presumed to extend far beyond the visible galactic disk, creating an invisible gravitational scaffold that shaped the orbital dynamics of satellite dwarf galaxies, influenced the trajectories of stellar streams produced by past merger events, and governed the overall architecture of the local group galaxy cluster, containing both Andromeda and our Milky Way system. Theoretical calculations based on cold dark matter, cosmological models predicted specific properties for these galactic dark matter halos, including their total masses, density distributions, substructure populations, and evolutionary histories, that could be tested through careful astronomical observations. Computer simulations of galaxy formation within cosmic dark matter frameworks generated detailed predictions about how these invisible halos should influence observable phenomena, including stellar kinematics, gas dynamics, gravitational lensing effects, and the statistical properties of satellite galaxy populations surrounding massive central systems like Andromeda. The standard cosmological model that emerged from these investigations, known as lambda cold dark matter, incorporates dark matter as an essential component comprising approximately 27% of the universe's total energy density, with ordinary atomic matter contributing less than 5%, while the remainder consists of an even more mysterious component called dark energy that drives cosmic acceleration. This framework achieved remarkable success in explaining numerous independent astronomical observations across vastly different scales, from the acoustic oscillations preserved in cosmic microwave background patterns to the statistical clustering properties of galaxy surveys spanning billions of light years, establishing dark matter as one of the fundamental pillars supporting contemporary understanding of cosmic evolution and structure formation throughout the observable universe. What happens when the most sophisticated computer model ever created to analyze galactic dynamics produces results that contradict 50 years of established cosmological theory? In February 2025, Francois Hammer and his international research team published groundbreaking findings in astronomy and astrophysics that sent shockwaves throughout the astronomical community, presenting evidence that Andromeda contains dramatically less dark matter than cosmological models predict for spiral galaxies of its size and stellar mass. This revolutionary analysis employed unprecedented computational sophistication, incorporating detailed merger history reconstructions, chemical evolution modeling, and dynamical simulations that accounted for the violent gravitational interactions that shaped Andromeda's current structure over billions of years of cosmic evolution. Unlike previous studies that assumed Andromeda represented a relatively undisturbed spiral galaxy, evolving smoothly since its formation, Hammer's team recognized that major merger events fundamentally alter galactic properties in ways that invalidate traditional mass estimation techniques based on equilibrium assumptions. Their methodology required developing entirely new theoretical frameworks capable of modeling how massive galactic collisions redistribute stellar populations, heat galactic disks, and modify the relationships between visible matter distributions and underlying gravitational potentials that govern stellar orbital dynamics throughout galactic systems. The research team painstakingly reconstructed Andromeda's merger history using observational evidence from stellar streams, shell structures, chemical abundance patterns, and kinematic signatures that preserve fossil records of ancient gravitational disruptions within contemporary stellar populations. Advanced M-body simulations incorporating hydrodynamic gas physics, stellar evolution processes, and chemical enrichment cycles enabled the researchers to predict how Andromeda's current observational properties should relate to its total mass content if standard dark matter models accurately describe cosmic structure formation processes. The shocking results revealed that Andromeda's total mass, including both visible and invisible components, measures significantly lower than cosmological simulations predict for galaxies possessing Andromeda's stellar mass, chemical composition, and structural characteristics. Detailed analysis of stellar kinematics, rotation curve measurements, and satellite galaxy orbital properties consistently indicated a dark matter halo containing approximately half the mass that lambda cold dark matter models require to explain galaxy formation within the cosmic web of primordial density fluctuations. This dramatic discrepancy cannot be explained through observational uncertainties or measurement errors, as multiple independent analysis techniques converged on the same conclusion using different datasets, methodological approaches, and theoretical assumptions about galactic structure and evolution processes. The implications cascade through every level of cosmological understanding, challenging fundamental assumptions about dark matter physics, cosmic structure formation, and the processes governing how galaxies acquire and retain their matter content throughout cosmic history. If Andromeda truly possesses insufficient dark matter to match theoretical predictions, then either our understanding of dark matter properties requires major revision, or galaxy formation processes operate differently than current models assume, possibly involving exotic physics, modified gravitational dynamics, or previously unrecognized feedback mechanisms that prevent galaxies from accumulating the full quota of dark matter that cosmological simulations assign to their host halos. The research findings suggest that massive merger events might somehow strip dark matter from galactic systems more efficiently than previously recognized, or that the relationship between visible matter and dark matter within individual galaxies differs substantially from the cosmic average values inferred from large-scale structure observations and cosmic microwave background measurements. Alternative explanations involve modified gravity theories that eliminate the need for dark matter entirely, though such models face significant challenges in explaining other astronomical observations that strongly support dark matter's existence within cosmic structure. Formation scenarios. The dark matter deficit discovery forces astronomers to confront uncomfortable questions about whether their understanding of cosmic evolution accurately describes reality, or whether fundamental physics operates differently on galactic scales than laboratory experiments and cosmological observations suggest. This revolutionary finding joins a growing collection of observational anomalies that challenge standard cosmological models, including the tension between different measurements of cosmic expansion rates, the unexpected smoothness of cosmic microwave background fluctuations, and the failure to detect dark matter particles despite decades of increasingly sensitive experimental searches conducted in underground laboratories worldwide. Hammer's analysis represents more than just another scientific paper questioning established theories. It potentially signals the beginning of a paradigm shift comparable to the discoveries that led to dark matter's original proposal, forcing the astronomical community to reconsider fundamental assumptions about cosmic architecture and the invisible scaffolding that supposedly governs universal structure formation processes. What forensic evidence allows astronomers to reconstruct cosmic crimes that occurred billions of years ago, piecing together galactic murder mysteries from scattered stellar remains? Deep within Andromeda's seemingly peaceful halo region, astronomers have discovered one of the most spectacular examples of galactic violence ever documented. A massive stellar stream extending more than 300,000 light-years across space, creating a ghostly ribbon of ancient stars that tells the story of a smaller galaxy's complete destruction. This enormous structure, known as the Giant Stellar Stream, represents the gravitational autopsy of a cosmic catastrophe that unfolded over hundreds of millions of years as tidal forces gradually dismantled an entire galactic system, scattering its stellar population across vast volumes of intergalactic space. The stream's discovery revolutionized our understanding of how large galaxies grow through cannibalistic processes, consuming their smaller neighbours and incorporating their stellar content into ever-expanding gravitational territories. Forensic astronomy techniques enable researchers to read these cosmic crime scenes with remarkable precision, using stellar positions, velocities, chemical compositions, and age distributions to reconstruct the sequence of events that led to complete galactic annihilation. Each star within the giant stellar stream carries unique fingerprints that reveal details about its birth environment, nuclear evolution history, and the gravitational circumstances that ejected it from its original galactic home into the cold expanses surrounding Andromeda's main stellar disk. The breadcrumb analogy provides an excellent framework for understanding how disrupted galaxies leave permanent traces of their existence, scattered throughout the halos of their gravitational captors. Just as a trail of breadcrumbs can guide travellers back to their own starting point, stellar streams preserve navigational information that allows astronomers to trace backwards through time, following these cosmic pathways to identify when, where, and how the original satellite galaxy met its destructive fate. Advanced computer simulations can model the complex gravitational interactions between massive host galaxies and their smaller companions, predicting exactly how tidal forces should stretch, twist, and ultimately shred satellite systems while distributing their stellar contents along specific orbital trajectories that depend on the collision geometry, relative velocities, and mass ratios involved in these cosmic encounters. The giant stellar stream's remarkable length exceeds the diameter of our entire local group galaxy cluster, demonstrating the enormous spatial scales over which galactic destruction events can distribute stellar material throughout cosmic space. This extended structure maintains coherent kinematic properties despite its vast dimensions, with constituent stars sharing similar orbital characteristics that clearly identify them as members of a single, disrupted stellar system, rather than random background populations that happen to align by cosmic coincidence. Spectroscopic analysis reveals that stream stars possess distinctive chemical abundances that differ significantly from Andromeda's indigenous stellar populations, providing additional evidence for their external origin and enabling astronomers to estimate the mass, metallicity, and star formation history of the destroyed progenitor galaxy. The discovery of such extensive tidal debris around Andromeda highlights a fundamental difference between our galactic neighbour's evolutionary path and the relatively quiet accretion history that characterises our own Milky Way's development over the past several billion years. While our galaxy has experienced minor merger events and continues to disrupt small satellite systems like the Sagittarius dwarf galaxy, Andromeda's halo contains evidence for much more violent interactions involving substantially larger galactic systems capable of producing the massive stellar streams observed in contemporary surveys. This divergence in merger histories reflects the stochastic nature of cosmic structure formation, where random encounters between galaxies within the expanding cosmic web create unique evolutionary trajectories that shape each system's final properties through complex sequences of accretion, disruption, and gravitational reorganization events. The giant stellar stream represents only the most prominent example of Andromeda's turbulent past. As detailed photometric surveys continue revealing additional tidal features, shell structures, and kinematic subgroups that provide evidence for multiple merger episodes spanning billions of years of galactic evolution. These observations transform our perception of Andromeda from a pristine spiral galaxy to a cosmic battlefield where gravitational warfare has raged throughout its existence, leaving permanent scars within its stellar populations that preserve detailed records of every major encounter with neighbouring galactic systems throughout the long history of local group formation and evolution processes. What cosmic catastrophe transformed the third largest member of our local group galaxy cluster into scattered stellar debris, while reshaping Andromeda's entire structural architecture? Approximately 2 billion years ago, during an epoch when Earth's early atmosphere still lacked significant oxygen and complex life remained confined to primitive microbial forms, our galactic neighbourhood witnessed one of the most dramatic collision events in local group history. Advanced reconstructions of Andromeda's merger chronology reveal compelling evidence for a massive galactic encounter involving a substantial spiral system possessing roughly 20 billion solar masses worth of stars, gas, and dark matter components. This colossal progenitor galaxy, now referred to by astronomers as the third giant due to its enormous size relative to contemporary local group members, approached Andromeda along a highly eccentric orbital trajectory that culminated in a devastating head-on collision capable of completely restructuring both galactic systems through the gravitational forces operating on scales that dwarf any terrestrial analogy. Cosmological simulations indicate that this ancient merger involved a galaxy comparable in mass to modern-day systems like the Large Magellanic Cloud, but scaled upward by the factors of 10 or more, representing a galactic titan whose destruction required hundreds of millions of years to complete, as tidal forces gradually dismantled its spiral arms, dispersed its stellar populations, and scattered its interstellar medium throughout Andromeda's expanding gravitational domain. The scale of destruction defies easy comprehension, involving the complete annihilation of a stellar system that had, presumably, evolved for billions of years, developing its own unique stellar populations, chemical enrichment patterns, and structural characteristics before encountering Andromeda's overwhelming gravitational influence. This massive merger event ranks among the most significant galactic interactions that have occurred within our local cosmic neighbourhood throughout the entire history of the universe, comparable to the eventual collision predicted between Andromeda and our own Milky Way system several billion years in the future. The gravitational violence associated with such encounters triggers spectacular bursts of star formation as interstellar gas clouds collide and compress, creating the intermediate-age stellar populations that astronomers now observe scattered throughout Andromeda's halo regions in configurations that clearly indicate external rather than indigenous origins. Computer models of the merger process predict that the incoming galaxy's stellar populations should have been distributed asymmetrically throughout Andromeda's halo, creating the distinctive spatial patterns and kinematic signatures that match detailed observations of contemporary stellar stream structures, shell features, and chemical abundance gradients measured by modern astronomical surveys. Perhaps most intriguingly, this ancient collision may have left behind a surviving remnant in the form of M32, Andromeda's peculiar elliptical companion galaxy that exhibits several unusual characteristics suggesting a violent evolutionary history. M32 possesses an exceptionally compact structure, high stellar density, and chemical composition patterns that differ substantially from typical elliptical galaxies of similar mass, leading astronomers to propose that it represents the stripped nuclear core of the original third giant that somehow survived the collision process while losing most of its extended stellar envelope to Andromeda's tidal forces. This interpretation explains M32's anomalous properties, while providing a concrete example of how major merger events can produce unexpected galactic remnants that preserve partial records of their tumultuous formation histories. The survival of a dense central core through such extreme gravitational disruption requires very specific initial conditions, including the progenitor's internal structure, the collision geometry, and the relative velocities involved in the encounter, making M32 a valuable fossil specimen that constrains theoretical models of galactic merger physics and outcomes. Advanced spectroscopic studies of M32's stellar populations reveal chemical fingerprints consistent with formation within a much larger galactic system, supporting the hypothesis that this compact object represents the sole surviving fragment of a once magnificent spiral galaxy that contributed most of its stellar content to Andromeda's current halo structure. The merger chronology suggests that this catastrophic event coincided with a period of enhanced star formation activity throughout Andromeda's disk regions, as the gravitational disturbances triggered by the collision compressed existing gas reservoirs and initiated widespread stellar nursery formation that continued for several 100 million years after the initial encounter. This correlation between merger timing and star formation episodes provides additional evidence linking the ancient collision with observable consequences that persist within Andromeda's contemporary stellar populations, chemical abundance patterns, and overall galactic architecture that continues bearing the structural scars of this ancient cosmic catastrophe even 2 billion years after its violent conclusion. How do astronomers decode the permanent scars left by ancient galactic collisions through precise measurements of stellar motions, ages, and chemical compositions scattered throughout Andromeda's complex architecture? Within Andromeda's stellar disk, detailed kinematic surveys reveal something extraordinary. Stars exhibit much higher random velocities than expected for a galaxy that evolved peacefully through gradual accretion processes. This phenomenon, known as a kinematically hot disk, indicates that stellar orbits have been significantly disturbed from their original circular trajectories around the galactic center, creating a three-dimensional velocity distribution that preserves dynamical memories of violent gravitational encounters. Normal spiral galaxy disks maintain thin, cold configurations, where stars follow nearly circular orbits with minimal vertical excursions. But Andromeda's stellar populations display velocity dispersions elevated far above theoretical predictions for undisturbed galactic evolution. These enhanced random motions represent direct evidence that powerful external forces injected substantial amounts of kinetic energy into the stellar system, heating the galactic disk through gravitational interactions that scattered individual stellar orbits out while preserving the overall rotational structure. Spectroscopic analysis of stellar ages throughout Andromeda's disk reveals another compelling piece of forensic evidence. Intermediate-age stellar populations appear in spatial locations where galactic evolution models predict only ancient or very young stars should exist. Standard theories of spiral galaxy development suggest that star formation should proceed in orderly waves, creating predictable age gradients that correlate with galactocentric distance and position within spiral arm structures. However, Andromeda's stellar archaeology tells a different story, with 7 to 10 billion-year-old stars scattered throughout regions that should contain either primordial stellar populations formed during the galaxy's initial assembly, or recent stellar generations born within contemporary star-forming complexes. This age distribution anomaly cannot be explained through internal galactic processes alone, requiring external perturbations capable of redistributing existing stellar populations while simultaneously triggering burst episodes of star formation that created new stellar cohorts during periods of gravitational disruption. Deep photometric surveys extending far into Andromeda's halo regions have revealed intricate shell structures that represent some of the most beautiful and scientifically valuable evidence for ancient merger events preserved within galactic architecture. These concentric features appear as subtle overdensities of stellar material arranged in nested patterns, reminiscent of ripples spreading across a cosmic pond after a massive gravitational stone was dropped into the galactic center. Computer simulations of galaxy mergers predict exactly these types of shell formations as natural consequences of phase-space mixing processes that occur when satellite galaxies are tidally disrupted and their stellar contents settle into quasi-equilibrium configurations within the host galaxy's gravitational potential well. The shell's spatial distribution, surface brightness profiles, and geometric properties provide detailed constraints on the merger event's timing, mass ratio, orbital characteristics, and collision geometry that produce these remarkable fossil structures. Each shell represents material deposited during specific phases of the merger process, creating a temporal sequence that astronomers can read like geological strata to reconstruct the chronological progression of galactic destruction and accretion. Perhaps the most definitive evidence for Andromeda's violent merger history comes from detailed chemical analysis of stellar populations distributed throughout its extended halo system. Spectroscopic measurements reveal that halo stars possess significantly higher metallicities than theoretical models predict for stellar populations formed through smooth galactic evolution within primordial cosmic environments. The enhanced heavy element abundances indicate that these stars formed within galactic systems that had already experienced substantial chemical enrichment through multiple generations of stellar evolution, supernova explosions, and the complex nucleosynthetic processes that transform primordial hydrogen and helium into the diverse atomic inventory observed in contemporary stellar atmospheres. This metal-rich stellar halo composition provides a chemical fingerprint that clearly identifies these stellar populations as immigrants from external galactic systems rather than indigenous stars formed within Andromeda's original gravitational territory. The metallicity distribution exhibits spatial patterns and abundance gradients that match theoretical predictions for stellar material stripped from a massive satellite galaxy during prolonged tidal interactions, creating the characteristic signatures that distinguish accreted stellar populations from in situ stellar formation products. Advanced stellar spectroscopy also reveals distinctive alpha element enhancement patterns that reflect the star formation histories and chemical evolution pathways experienced by the disrupted progenitor galaxy before its incorporation into Andromeda's halo structure, providing additional evidence for the external origin of these metal-enriched stellar populations that now comprise a substantial fraction of Andromeda's total stellar mass inventory. What invisible cosmic scaffolding extends Andromeda's gravitational influence across distances that dwarf its brilliant spiral disk, harbouring ancient stellar populations that preserve the earliest chapters of galactic history? Far beyond the luminous boundaries where Andromeda's spiral arms fade into darkness, an enormous stellar halo stretches across hundreds of thousands of light years, creating a vast three-dimensional structure that contains crucial evidence about galaxy formation processes operating throughout cosmic time. This extended stellar envelope represents one of the most challenging astronomical targets to study, as its constituent stars scatter such faint light across such enormous volumes that detecting individual sources requires the most sensitive instruments available to modern astronomy. Yet within this tenuous stellar atmosphere lies a treasure trove of information about how massive galaxies assemble their matter, interact with cosmic environments, and preserve fossil records of their evolutionary histories within stellar populations that span the entire age of the universe. Recent surveys using advanced photometric techniques have revealed that Andromeda's stellar halo actually consists of two distinct components with dramatically different properties, origins, and spatial distributions that tell complementary stories about galactic evolution pathways. The inner component forms a roughly spherical configuration of ancient metal-poor stars that likely represents the original stellar population formed during Andromeda's initial gravitational collapse from primordial gas clouds billions of years ago. These primordial stellar citizens exhibit the chemical signatures expected for early cosmic star formation, with low heavy element abundances reflecting the universe's pristine composition before successive generations of stellar nucleosynthesis enriched the interstellar medium with carbon, oxygen, silicon, iron, and other elements essential for planetary formation and biological processes. The outer halo component displays entirely different characteristics, showing clear evidence for external origins through its flattened spatial distribution, enhanced metallicity levels, and complex kinematic properties that indicate formation within previously independent galactic systems. This accreted stellar population represents the accumulated debris from numerous minor merger events and satellite galaxy disruptions that occurred throughout Andromeda's evolutionary history, creating a cosmic archaeological record of galactic cannibalism preserved within stellar fossils scattered across the local group's gravitational landscape. Detailed analysis of metallicity gradients throughout the halo system reveals systematic changes in stellar chemical composition that reflect the complex interplay between internal galactic evolution and external accretion processes operating across different cosmic epochs. The most metal-poor populations occupy the halo's outermost regions, where stellar densities drop to levels barely distinguishable from intergalactic background, suggesting these ancient systems formed during the earliest phases of cosmic structure formation, when heavy element production remained minimal throughout the universe. Intermediate metallicity populations dominate the middle halo regions, representing stellar material accreted from satellite galaxies that experienced moderate levels of chemical enrichment before their gravitational capture and subsequent disruption by Andromeda's tidal forces. The highest metallicity halo stars concentrate within inner regions closer to the galactic disk, indicating either the late-stage accretion of chemically evolved satellite systems or radial migration of deck stars heated by gravitational interactions into halo-like orbital configurations. Age stratification patterns throughout the stellar halo provide additional constraints on Andromeda's assembly timeline, with the oldest stellar populations concentrated in the most extended halo regions where gravitational binding energies remain weakest and dynamical timescales exceed the current age of the universe. These ancient stellar systems, approaching 14 billion years in age, formed when the cosmic microwave background radiation still glowed at temperatures sufficient to ionize hydrogen atoms, and the universe contained only trace quantities of elements heavier than lithium. Intermediate age populations displaying ages between 8 and 12 billion years populate the middle halo, regions corresponding to cosmic epochs when galaxy formation activity peaked throughout the universe and merger rates reached maximum values within cosmic structure formation scenarios. The youngest halo populations, surprisingly, appear concentrated within inner regions where ongoing accretion events continue depositing stellar material stripped from contemporary satellite galaxies that orbit within Andromeda's gravitational sphere of influence. This age-radius relationship demonstrates how galactic halos grow through inside-out assembly processes, with successive accretion episodes depositing progressively younger stellar populations at larger radial distances, while earlier generations settle into more centrally concentrated configurations through gravitational dynamical evolution, operating over cosmic timescales that span billions of years of continuous galactic growth and structural reorganization. What hidden galactic ecosystems continue revealing themselves as astronomical? Surveys push deeper into the faint outskirts of Andromeda's gravitational domain, uncovering an entire population of cosmic inhabitants previously invisible to human detection. In February 25, astronomers announced the discovery of Pegasus 7, a remarkably faint dwarf galaxy lurking at the very edge of detectability within Andromeda's extended gravitational sphere, representing one of the most elusive galactic systems ever identified through systematic photometric surveys. This ghostly stellar collection, containing fewer than 30,000 solar masses worth of star stairs distributed across several thousand light-years of space, demonstrates how much we still don't know about the complete census of galactic objects populating our local cosmic neighbourhood. Pegasus 7's discovery required sophisticated computer algorithms capable of identifying subtle stellar overdensities against the complex background of foreground Milky Way stars, background galaxies, and instrumental artifacts that contaminate deep astronomical imaging datasets. The newly found system exhibits extreme properties that challenge theoretical models of dwarf galaxy formation, possessing such low surface brightness that it remained completely invisible until advanced data processing techniques revealed its presence through statistical analysis of stellar color and magnitude distributions across multiple photometric bands. This discovery brings Andromeda's known satellite population to more than 20 confirmed dwarf galaxy companions, each representing a unique gravitational laboratory where astronomers can study galaxy formation processes operating on the smallest scales accessible to detailed observational investigation. These diminutive galactic systems span an enormous range of physical properties, from relatively massive satellites like M32 and M110 that retain active star formation capabilities, to ultra-faint systems barely distinguishable from large globular star clusters in terms of their stellar, content, and luminosity characteristics. The satellite population exhibits a striking diversity in chemical composition, stellar ages, morphological substructures, and orbital configurations that reflects the complex variety of formation mechanisms and evolutionary pathways available to low-mass galactic systems within the cosmic web of dark matter, halos, and gravitational interactions. Many of these dwarf galaxies show clear signs of ongoing tidal disruption, as Andromeda's powerful gravitational field gradually strips away their outer stellar populations, creating extended stellar streams that trace the orbital trajectories followed by these doomed satellite systems during their final approaches toward complete gravitational dissolution. The process of galactic cannibalism continues operating today at measurable rates, with several satellite galaxies currently undergoing active tidal stripping that redistributes their stellar content throughout Andromeda's halo regions while gradually reducing their bound masses below the threshold necessary for maintaining independent gravitational existence. This ongoing accretion process demonstrates that galaxy building represents a continuous phenomenon rather than an ancient historical episode, with massive systems like Andromeda continuing to grow through the systematic capture and digestion of smaller galactic neighbours throughout the present cosmic epoch. Advanced surveys mapping the spatial distribution of stellar streams throughout Andromeda's halo reveal intricate networks of tidal debris that connect disrupted satellite systems with their current orbital positions, creating a complex tapestry of gravitational archaeology that preserves detailed information about past merger events and dynamical interactions. These stellar stream systems exhibit remarkable coherence across enormous spatial scales, maintaining recognizable kinematic signatures and chemical abundance patterns despite being stretched across hundreds of thousands of light-years of space through differential gravitational forces operating over millions of years of orbital evolution. Computer simulations predict that most observed stellar streams should eventually fade below detectability thresholds as continued gravitational stirring disperses their stellar content throughout the general halo population, making current observations particularly valuable for constraining the timing and characteristics of recent satellite disruption events. These stream mapping campaigns also reveal previously unknown tidal features associated with satellite galaxies that have completely disappeared from direct observation, leaving only their stellar ghosts behind as testimony to Andromeda's voracious appetite for consuming smaller galactic systems. Future surveys utilizing next-generation telescopic capabilities promise to uncover even fainter dwarf galaxy populations and more extensive stellar stream networks, potentially doubling or tripling the known satellite census while revealing the complete three-dimensional architecture of tidal debris structures that document Andromeda's entire accretion history since galaxy formation began. These discoveries transform our understanding of how massive galaxies like Andromeda maintain their growth throughout cosmic time, revealing galactic evolution as an ongoing process of hierarchical assembly, where large systems continuously incorporate smaller building blocks while reshaping their internal structure through gravitational interactions that operate across the entire spectrum of cosmic scales, from individual stellar orbits to the largest dark matter halos. How does the invisible scaffolding of dark matter arrange itself around massive galaxies, and why does Andromeda's dark matter geography contradict everything astronomers expected to find based on cosmological computer models? Advanced analysis of stellar motions throughout Andromeda's extended regions reveals that its dark matter halo possesses a surprisingly spherical configuration, deviating significantly from the flattened triaxial structures predicted by sophisticated numerical simulations of cosmic structure formation within cold dark matter frameworks. This geometric discrepancy suggests either that theoretical models incompletely capture the physics governing dark matter halo evolution, or that observational techniques systematically bias measurements toward detecting more spherical configurations than actually exist within galactic systems. The spherical halo geometry contrasts sharply with predictions from cosmological n-body simulations that consistently produce elongated dark matter distributions reflecting the anisotropic gravitational collapse processes that shape cosmic structure formation across all observable scales, from galaxy clusters down to individual galactic systems. Detailed gravitational modelling incorporating both stellar kinematics and satellite galaxy orbital dynamics indicates that Andromeda's total mass, including both visible and dark components, falls substantially below theoretical expectations for galaxies possessing its observed stellar mass, luminosity, and structural characteristics. This mass deficit represents more than a simple measurement uncertainty, as multiple independent analysis techniques converge on the same conclusion using different datasets, methodological approaches, and theoretical assumptions about galactic structure and gravitational dynamics. The reduced dark matter content fundamentally alters local group dynamics, affecting predictions for the eventual gravitational interaction between Andromeda and our Milky Way system, while potentially explaining observed peculiarities in satellite galaxy populations and stellar stream morphologies that have puzzled astronomers for decades. Lower total masses translate into weaker gravitational binding forces, modified orbital decay, timescales for satellite systems, and altered tidal shown disruption rates that influence how quickly smaller galaxies lose their stellar content to the host system's gravitational field. These dynamical consequences ripple throughout the entire local group architecture, changing the predicted collision timeline between major galactic members, while potentially resolving discrepancies between observed satellite populations and theoretical predictions based on standard cosmological models. Future investigations using NASA's Nancy Grace Roman Space Telescope promise revolutionary advances in dark matter detection through unprecedented surveys of stellar stream systems throughout Andromeda's extended halo regions, where gravitational interactions with dark matter substructures should produce characteristic observational signatures detectable through precise stellar position and velocity measurements. Roman's wide-field imaging capabilities will enable systematic mapping of stellar streams extending across hundreds of thousands of light-years, achieving sufficient spatial resolution to detect gaps, density variations, and kinematic perturbations that reveal the presence of otherwise invisible dark matter clumps embedded within galactic halo systems. These dark matter subhalos represent fundamental predictions of hierarchical structure formation models, where cosmic web filaments fragment into progressively smaller gravitational units that survive as distinct entities within larger dark matter concentrations surrounding massive galaxies. Computer simulations predict that typical galactic dark matter halos should contain thousands of subhalo systems spanning enormous mass ranges, from dwarf galaxy scales down to objects comparable to globular star clusters, creating a complex three-dimensional network of gravitational perturbations that influence stellar stream evolution through repeated close encounters and tidal heating episodes. The detection of gaps within stellar streams provides one of the most promising techniques for directly observing dark matter physics, as these disruptions preserve fossil evidence for gravitational interactions with invisible subhalo populations that cannot be detected through electromagnetic radiation, but leave permanent imprints within the phase space distributions of disrupted stellar systems. Roman telescope observations will achieve sufficient precision to measure stellar stream properties with unprecedented accuracy, enabling detection of velocity perturbations, spatial discontinuities, and morphological distortions that reveal dark matter, subhalo encounters occurring over millions of years of orbital evolution within galactic gravitational potentials. The gap detection method offers unique advantages for dark matter research because it probes gravitational effects rather than uncertain particle physics predictions, providing model-independent constraints on dark matter, clustering properties, interaction cross-sections, and the small-scale power spectrum that determines cosmic structure formation outcomes across all observable scales. Successful identification of multiple stellar stream gaps would confirm theoretical expectations for hierarchical dark matter assembly, while providing detailed measurements of subhalo masses, spatial distributions, and encounter rates that directly test fundamental assumptions underlying contemporary cosmological paradigms governing universal evolution since cosmic dawn. How does a single galaxy's unexpected dark matter shortage send shockwaves through our understanding of cosmic evolution, forcing astronomers to reconsider the fundamental composition and structure of the entire observable universe? Andromeda's reduced dark matter content creates a cascade of consequences that extend far beyond individual galactic physics, challenging the delicate balance of cosmic ingredients that cosmologists have spent decades carefully calibrating to explain everything from primordial nucleosynthesis to large-scale structure. Formation patterns observed across billions of light-years. The missing baryon problem becomes even more perplexing when galaxies like Andromeda contain insufficient dark matter to gravitationally retain the full quota of ordinary atomic matter that Big Bang nuclear synthesis calculations predict should exist within cosmic environments. Standard cosmological models require precise ratios between dark matter, ordinary matter, and dark energy components to successfully reproduce observed features in the cosmic microwave background radiation, galaxy clustering statistics, and the chemical abundance patterns measured in ancient stellar populations throughout the universe. If substantial numbers of galaxies possess dark matter deficits similar to Andromeda's newly discovered shortage, then the cosmic matter budget requires fundamental recalibration that could invalidate decades of carefully constructed theoretical frameworks designed to explain universal evolution from primordial quantum fluctuations to contemporary galactic architecture. Galaxy formation theories built upon cold dark matter foundations assume that massive galactic systems like Andromeda should contain approximately 5 times more dark matter than ordinary atomic matter, creating the gravitational scaffolding necessary for efficient gas accretion, stellar formation regulation, and the hierarchical assembly processes that transform primordial density perturbations into the rich tapestry of cosmic structures observed throughout the contemporary universe. Andromeda's apparent violation of these mass ratios suggests either that galaxy formation physics operates differently than theoretical models assume, or that dark matter itself possesses properties not incorporated within standard cosmological scenarios, potentially requiring exotic particle physics, modified gravitational dynamics, or previously unrecognized feedback mechanisms that prevent galaxies from accumulating their predicted dark matter. Quotas. The implications for local group dynamics prove equally dramatic, as reduced total masses for both Andromeda and potentially our own Milky Way system fundamentally alter gravitational interaction timescales, orbital decay rates, and the predicted collision scenario that has captivated astronomical imagination for decades. Previous calculations based on standard dark matter assumptions predicted that Andromeda and the Milky Way would experience a catastrophic gravitational encounter within approximately 4 billion years, completely reshaping both galactic systems through tidal disruption, stellar scattering, and the eventual merger of their central supermassive black holes into a single massive gravitational singularity. However, if both galaxies contain significantly less dark matter than assumed, their reduced gravitational binding energies and modified orbital characteristics could postpone this cosmic collision indefinitely, transforming what seemed like inevitable galactic destruction into a cosmic near-miss that preserves both systems as independent stellar cities throughout the remaining lifetime of stellar evolution within the observable universe. The uncertainty extends beyond collision timing to encompass fundamental questions about how galaxies acquire their matter content, maintain structural stability, and interact with surrounding cosmic environments throughout billions of years of continuous evolution within the expanding space-time framework that governs universal dynamics. Contemporary observations of galaxy properties across cosmic history rely heavily upon theoretical assumptions about dark matter, distribution patterns, gravitational clustering amplitudes, and the relationship between visible matter and total mass content that enable astronomers to interpret redshift surveys, gravitational lensing measurements, and stellar population characteristics observed in distant galactic systems. If these foundational assumptions prove incorrect, then significant portions of observational cosmology require reinterpretation, using revised theoretical frameworks that accommodate different dark matter, physics, alternative gravitational theories, or complex baryon feedback processes capable of dramatically altering the relationship between visible galactic properties and underlying gravitational mass distributions. The universe's fundamental constants, including the critical density parameter that determines cosmic geometry, the matter-energy ratios that govern expansion dynamics, and the dark matter interaction cross-sections that control structure formation efficiency, all face potential revision. If Andromeda's anomalous properties represent typical rather than exceptional characteristics of massive galactic systems throughout the observable cosmos, what happens when a cosmic catastrophe that astronomers considered inevitable suddenly becomes a cosmic coin flip, transforming our understanding of the local group's ultimate fate? For decades, precise measurements of Andromeda's motion through space convinced researchers that our galactic neighbour was approaching on an unstoppable collision course that would culminate in spectacular destruction approximately 4.5 billion years from now, creating one of the most anticipated astronomical events in cosmic history. This prediction became so widely accepted that scientists confidently described the eventual merger scenario in exquisite detail. Spiral arms would be torn apart by gravitational forces, stellar systems would be flung into intergalactic space, massive gas clouds would collide and trigger unprecedented bursts of star formation, and the central supermassive black holes would eventually spiral together in a final gravitational wave crescendo that would reshape the fabric of space-time itself. Sophisticated computer simulations generated beautiful visualizations of this galactic apocalypse, showing how two magnificent spiral systems would dance together through a prolonged death spiral lasting hundreds of millions of years before finally merging into a single massive elliptical galaxy that astronomers playfully nickname Andromeda. However, recent recalculations incorporating Andromeda's reduced mass estimates and more precise measurements of its transverse velocity components have dramatically altered this seemingly certain future, revealing that the probability of actual collision may be no better than 50%. The revised calculations account for previously overlooked factors including measurement uncertainties in Andromeda's proper motion, the gravitational influence of the Triangulum galaxy, and the complex three-body dynamics that govern orbital evolution within our local group gravitational system. Advanced computational models incorporating these refinements demonstrate that small changes in initial conditions can produce vastly different outcomes, with some simulation runs resulting in spectacular galactic mergers, while others show the two spiral systems executing an elegant gravitational ballet that brings them close enough for dramatic tidal interactions before sending them back into separate orbital trajectories. The gravitational choreography becomes even more intricate when considering Triangulum's role as the third major player in this cosmic drama, exerting subtle but potentially crucial influences on the orbital mechanics that determine whether Andromeda and the Milky Way will ultimately embrace or merely exchange gravitational pleasantries during their closest approach billions of years hence. Triangulum's gravitational perturbations introduce additional complexity into what initially appeared to be a straightforward two-body problem, creating chaotic dynamics where tiny variations in current velocities and positions can amplify over cosmic timescales to produce completely different evolutionary outcomes. The three-galaxy system resembles a cosmic version of the classical three-body problem that has challenged mathematical physicists for centuries, where analytical solutions prove impossible and numerical integrations reveal exquisitely sensitive dependence on initial conditions that makes long-term predictions inherently uncertain despite the deterministic nature of gravitational physics. This gravitational uncertainty principle operating on galactic scales transforms our cosmic neighbourhood's future from a predetermined destiny into an open question that will only be resolved through billions of years of actual orbital evolution that no human civilization will survive to witness. The poetic irony of this astronomical revelation cannot be overlooked. Our nearest galactic neighbour, the cosmic companion that has inspired countless generations of stargazers and served as astronomy's primary laboratory for understanding spiral galaxy physics, may indeed remain our neighbour, indefinitely rather than becoming our destroyer and merger partner in some distant cosmic epoch. This possibility fundamentally alters humanity's perspective on cosmic timescales and the longevity of galactic structures, suggesting that the beautiful spiral patterns we observe today might persist far longer than previously imagined, continuing to grace the nighttime sky for conscious beings that may evolve billions of years in the future on worlds we cannot yet imagine. The near-miss scenario presents its own fascinating astronomical consequences, as the close gravitational encounter would still trigger significant structural changes in both galactic systems even without direct merger, potentially disrupting stellar orbits, triggering starburst episodes, and reshaping spiral arm patterns, while preserving the essential architectural integrity that makes each galaxy a unique stellar ecosystem. Future observations using next-generation astrometric satellites will gradually refine these probability estimates by measuring Andromeda's motion with unprecedented precision, slowly resolving the cosmic uncertainty that currently governs our understanding of the local group's ultimate gravitational destiny, and determining whether our galactic home will face destruction, transformation, or preservation across the vast temporal expanses that separate our current epoch from the distant future, when stellar evolution itself begins approaching its final chapters throughout the observable universe. What technological marvels enable modern astronomers to decode galactic histories, spanning billions of years, transforming scattered points of starlight into detailed reconstructions of cosmic violence and evolution. Hubble Space Telescope stands as perhaps the greatest astronomical instrument ever conceived, accumulating more than 3 decades of continuous observations that have revolutionized our understanding of galactic structure, stellar evolution, and cosmic architecture through unprecedented clarity achieved above Earth's turbulent atmospheric interference. This orbital observatory's remarkable longevity has enabled systematic monitoring of Andromeda's stellar populations across timescales sufficient to detect subtle changes in stellar brightness, discover new variable stars, and track the proper motions of individual stellar sources moving within our neighbouring galaxy's gravitational field. Hubble's exquisite optical resolution, achieved through precision engineering that maintains focus stability measured in nanometers despite operating in the harsh space environment, allows astronomers to distinguish individual red giant stars, massive blue supergiants, and even some white dwarf remnants scattered throughout Andromeda's disk and halo regions at distances exceeding 2 million light-years. The telescope's multi-wavelength capabilities span from ultraviolet through near-infrared spectral regions, enabling detailed studies of stellar temperatures, chemical compositions, evolutionary stages, and the complex interstellar medium that connects stellar birth and death processes throughout galactic ecosystems. Complementing Hubble's imaging prowess, the Dark Energy Spectroscopic Instrument represents a revolutionary advance in multi-object spectroscopy, capable of simultaneously measuring precise radial velocities and chemical abundances for thousands of stellar sources distributed across enormous areas of sky during single observing sessions. DESI's innovative robotic fiber positioning system enables rapid reconfiguration between different target fields, allowing systematic surveys of stellar kinematics throughout Andromeda's extended regions, with unprecedented efficiency and statistical completeness. The instrument's spectroscopic precision reaches levels sufficient to detect velocity variations smaller than 1 km per second, revealing subtle gravitational perturbations, orbital motions, and kinematic substructures that preserve fossil evidence of ancient merger events within contemporary stellar populations. Advanced data processing algorithms extract detailed chemical fingerprints from stellar spectra, measuring abundances of carbon, nitrogen, oxygen, magnesium, silicon, calcium, titanium, iron, and numerous other elements that trace the nucleosynthetic history and formation environments experienced by individual stars throughout their evolutionary lifetimes. NASA's upcoming Nancy Grace Roman Space Telescope promises to extend these capabilities into entirely new observational territories, combining Hubble's optical precision with panoramic fields of view that exceed ground-based survey telescopes by enormous factors while maintaining space-based image quality throughout its operational lifetime. Roman's wide-field instrument will capture equivalent areas to hundreds of Hubble images in single exposures, enabling comprehensive mapping of stellar streams, dark matter substructure, and gravitational microlensing events across unprecedented spatial scales throughout our local sim. Group neighbourhood and beyond, the telescope's specialised coronagraphic capabilities will also pioneer direct detection techniques for exoplanetary systems around nearby stars, potentially revealing worlds orbiting within Andromeda's stellar populations if technological advances enable observations at such extreme distances. Perhaps most importantly, Roman's dark matter investigation capabilities will test fundamental cosmological predictions through systematic searches for gravitational perturbations within stellar stream systems that reveal invisible sub-halo populations embedded within galactic dark matter distributions. Computational astronomy has evolved into an indispensable partner for observational research, with sophisticated numerical simulations achieving sufficient complexity and resolution to reproduce detailed properties of observed galactic systems, including Andromeda's structural features, chemical abundance patterns, and kinematic signatures associated with ancient merger events. Modern N-body hydrodynamic codes incorporate realistic stellar evolution physics, chemical enrichment process, supernova feedback mechanisms, black hole accretion dynamics, and magnetic field effects that govern how galaxies assemble their mass, regulate star formation activity, and respond to gravitational interactions with the neighbouring systems throughout cosmic history. These computational models enable direct comparison between theoretical predictions and observational measurements, providing the interpretive framework necessary for understanding how complex astrophysical processes operating across enormous spatial and temporal scales combine to produce the galactic architectures we observe throughout the contemporary universe. Advanced algorithms running on supercomputer clusters can follow the evolution of millions of individual stellar particles through billions of years of simulated time, tracking how gravitational forces, stellar winds, supernova explosions, and tidal interactions reshape galactic structure while preserving detailed records of formation, histories that can be directly compared with archaeological evidence preserved within real stellar populations observed by modern telescopic surveys. Could the revolutionary discoveries about Andromeda's dark matter deficit and violent merger history represent universal principles governing galactic evolution throughout the cosmos, fundamentally changing how astronomers understand the formation and development of every spiral galaxy across billions of light years? Andromeda serves as our essential template for comprehending spiral galaxy physics, precisely because its proximity enables detailed investigations impossible to conduct with more distant galactic systems, where entire stellar populations appear as unresolved points of light and individual merger signatures become lost within observational noise and systematic uncertainties. Every measurement of Andromeda's stellar kinematics, chemical abundance gradients, dark matter distribution, and structural morphology provides crucial calibration data that astronomers apply to interpret observations of thousands of similar systems scattered throughout surveys spanning cosmic volumes that encompass billions of galaxies at distances where light travel times exceed half the current age of the universe. The implications of Andromeda's anomalous properties extend far beyond our local group, suggesting that standard theoretical models may systematically overestimate dark matter content within massive spiral galaxies throughout the observable cosmos, potentially requiring fundamental revisions to cosmological frameworks that govern our understanding of structure formation since the earliest epochs following cosmic recombination. Recent advances in observational astronomy reveal that merger-driven evolution represents the dominant pathway through which large galaxies acquire their mass, shape their morphological characteristics, and to develop the complex stellar population mixtures observed in contemporary galactic systems across all cosmic environments, from isolated field galaxies to dense cluster cores where gravitational interactions occur with enhanced frequency and violence. Unlike the peaceful gradual accretion scenarios that dominated earlier theoretical models of galaxy formation, modern observations consistently demonstrate that major merger events fundamentally reshape galactic architecture, trigger massive starbursts, redistribute stellar populations throughout extended halo regions, and leave permanent structural scars that persist for billions of years after the initial gravitational encounters conclude. Stellar archaeology emerges as one of the most powerful techniques for reconstructing cosmic history, enabling astronomers to read detailed chronicles of galactic evolution preserved within the spatial distributions, chemical compositions, kinematic properties, and age. Characteristics of stellar populations that span the entire temporal range from primordial star formation epochs to contemporary stellar nurseries where ongoing galaxy assembly processes continue operating throughout the present cosmic era. Each resolved star within Andromeda's vast stellar census carries unique fingerprints that encode information about its birth environment, nuclear evolution pathway, chemical enrichment history, and the gravitational circumstances that determined its current orbital configuration within the galaxy's three-dimensional architecture, creating an enormous database of fossil evidence that documents every significant episode in Andromeda's 13 billion-year evolutionary chronicle. The same stellar archaeological techniques applied to Andromeda's populations can be extended to other nearby galaxies within the local group, providing comparative studies that reveal how different initial conditions, environmental influences, and stochastic merger histories produce the remarkable diversity of galactic properties observed throughout the local cosmic neighbourhood and, by extension, similar galactic systems distributed throughout the broader universe. Universal physical processes governing stellar evolution, supernova nucleosynthesis, black hole accretion, magnetic field dynamics, and gravitational interactions operate identically throughout the cosmos, ensuring that the fundamental mechanisms shaping Andromeda's structure also determine the evolutionary pathways followed by spiral galaxies in distant cosmic environments where environmental conditions, dark matter halo properties, and merger frequencies may differ substantially from local group characteristics. Advanced spectroscopic surveys of distant galaxy populations reveal chemical abundance patterns, stellar population ages, and kinematic signatures that closely match those observed within Andromeda's stellar components, suggesting that the physical processes responsible for galactic assembly, chemical enrichment, and structural evolution maintain remarkable consistency across cosmic scales spanning billions of parsecs and temporal intervals encompassing most of universal history since galaxy formation began. The discovery that Andromeda contains less dark matter than theoretical models predict raises profound questions about whether similar dark matter deficits characterize other massive spiral galaxies throughout the universe, potentially indicating systematic flaws in cosmological simulations, incomplete understanding of baryon physics, or exotic dark matter. Properties not incorporated within standard particle physics frameworks that form the foundation for contemporary structure. Formation theories governing cosmic evolution from primordial quantum fluctuations to the rich galactic ecosystems observed throughout the contemporary universe. How might the discovery of insufficient dark matter within Andromeda signal the beginning of a cosmological revolution, comparable to the paradigm shifts that transformed astronomy during the 20th century, forcing scientists to reconsider fundamental assumptions about cosmic architecture and invisible matter? The accumulating evidence for dark matter deficits in massive galactic systems represents more than a simple observational anomaly requiring minor theoretical adjustments. Instead, it challenges the foundational pillars supporting contemporary cosmological models that have guided astronomical research for decades while achieving remarkable success in explaining diverse phenomena, from cosmic microwave background fluctuations to large-scale structure formation patterns observed across billions of light years. This paradigm adjustment forces astronomers to confront uncomfortable questions about whether their understanding of cosmic evolution accurately reflects reality, or whether fundamental physics operates differently on galactic scales than laboratory experiments and particle accelerator. Investigations suggest through decades of careful measurement and theoretical development. Alternative explanations for the apparent dark matter shortage span a broad spectrum of possibilities ranging from exotic modifications to Einstein's general relativity theory that eliminate the need for invisible matter entirely, to previously unrecognized astrophysical processes that prevent galaxies from accumulating their predicted dark matter quotas through mechanisms involving complex feedback interactions between ordinary matter, dark matter, and the cosmic web of filamentary structure connecting galactic systems throughout the observable universe. Modified gravity theories propose that gravitational forces behave differently on galactic and cosmological scales than Newton's inverse square law predicts, potentially explaining galactic rotation curves, cluster dynamics, and cosmic structure formation without requiring vast quantities of exotic particles that have remained undetected. Despite intensive experimental searches conducted in underground laboratories, particle colliders, and space-based detectors designed specifically to identify dark matter interaction signatures. However, these alternative gravitational frameworks face significant challenges in simultaneously explaining all astronomical observations that currently support dark matter's existence, including gravitational lensing effects, cosmic microwave background acoustic peaks, and the detailed statistical properties of galaxy clustering patterns that emerge from precision cosmological surveys spanning enormous cosmic volumes, containing millions of galactic systems across multiple epochs of universal evolution. The ongoing mystery deepens when considering that ordinary atomic matter comprises less than 15% of the universe's total energy density, leaving approximately 85% of cosmic contents completely invisible and fundamentally unidentified, despite representing the key dominant component governing structure formation, galactic dynamics, and the ultimate fate of cosmic expansion throughout the observable universe. This staggering ignorance about the universe's primary constituents remains one of the most profound gaps in scientific knowledge, comparable to discovering that terrestrial biology had overlooked the existence of an entire kingdom of life forms that actually comprised the majority of Earth's biomass while remaining completely undetected by conventional biological investigation techniques. Dark matter's elusive nature continues confounding experimental physicists who have constructed increasingly sophisticated detection apparatus designed to identify hypothetical dark matter particles through direct collision events, annihilation signatures, or decay products that might reveal the fundamental physics underlying this cosmic mystery that shapes everything from galactic formation to the large-scale architecture of cosmic structure spanning hundreds of millions of light-years. Future investigations utilizing NASA's Nancy Grace Roman Space Telescope promise unprecedented capabilities for probing dark matter physics through systematic surveys of gravitational microlensing events, stellar stream perturbations, and galaxy cluster weak lensing, measurements that will achieve statistical precision sufficient to distinguish between competing theoretical models while potentially revealing entirely new classes of dark matter candidates or gravitational phenomena not anticipated by current theoretical frameworks. Next-generation ground-based telescopic facilities, including the Vera Rubin Observatory and extremely large telescope projects, will complement space-based observations by conducting comprehensive surveys of galactic properties across cosmic history, measuring dark matter effects through gravitational lensing, stellar kinematics, and galaxy clustering analysis with unprecedented accuracy and statistical completeness that may finally resolve fundamental questions about cosmic matter content and gravitational physics operating throughout the universe. The convergence of these advanced observational capabilities with revolutionary computational techniques, including artificial intelligence algorithms capable of identifying subtle patterns within enormous datasets, promises to accelerate the pace of dark matter research while potentially uncovering unexpected connections between galactic properties, cosmic evolution, and fundamental physics that current theoretical models have failed to anticipate or incorporate within their predictive frameworks governing universal structure and evolution. What does it mean for humanity to exist within a cosmos that continuously reshapes itself through processes so vast and gradual that entire civilizations rise and fall while galaxies exchange single breaths in their billion-year respiratory cycles? The universe operates as an enormous recycling system where stellar material flows constantly between galactic systems through gravitational interactions, stellar winds, and explosive events that distribute heavy elements forged within stellar cores across intergalactic distances spanning millions of light years. Every carbon atom in your body, every oxygen molecule you breathe, and every iron nucleus flowing through your bloodstream originated within the nuclear furnaces of ancient stars that lived and died billions of years ago, possibly within galactic systems completely different from our current Milky Way home, before cosmic recycling processes transported these life-enabling elements across vast distances to become incorporated within the planetary materials that eventually formed Earth and enabled the emergence of biological complexity. Andromeda and our galaxy participate in this cosmic chemical exchange through stellar winds, supernova explosions, and the ongoing tidal stripping of satellite galaxies that continuously redistribute enriched material throughout local group space, ensuring that stellar nucleosynthesis products created within one galactic system eventually become available for star formation within neighbouring cosmic territories. The metals essential for planetary formation and biological processes travel these cosmic highways for billions of years, moving through interstellar and intergalactic space at velocities measured in hundreds of kilometers per second, while following gravitational currents that connect distant stellar populations through invisible networks of matter exchange operating across scales that dwarf human comprehension, yet ultimately enable our existence within this vast chemical circulation system. Cosmic evolution proceeds through hierarchical structure building where smaller gravitational units merge to form progressively larger systems, with galaxy formation representing intermediate steps within a universal construction project that began with quantum fluctuations in the primordial universe and continues today through ongoing accretion processes that add mass to galactic systems while triggering new episodes of star formation, chemical enrichment, and architectural reorganization. The merger events shaping Andromeda's current structure represent typical examples of cosmic construction processes operating throughout the observable universe, where gravitational forces orchestrate the assembly of increasingly complex cosmic ecosystems through billions of years of patient accumulation, violent collisions, and gradual settling into quasi-equilibrium configurations that maintain structural stability across cosmological timescales. These billion-year construction projects remain invisible to human perception except through sophisticated astronomical observations that freeze momentary snapshots of ongoing evolutionary processes, revealing cosmic dynamics in the same way that time-lapse photography captures the blooming of flowers by compressing hours of gradual change into seconds of visible transformation. Astronomers studying Andromeda observe the preserved consequences of events that occurred when Earth's atmosphere contained no oxygen and life remained confined to primitive microbial forms. Yet these ancient interactions continue influencing contemporary galactic structure through gravitational memory effects that persist across cosmic epochs, spanning the entire history of complex life on our planet. The temporal scales governing cosmic evolution challenge human intuition and perspective as processes that seem static and unchanging actually unfold with constant motion and transformation occurring too slowly for biological senses to detect without technological assistance that extends our perceptual capabilities across spatial and temporal dimensions far beyond those accessible to direct experience. Within this dynamic cosmic context, human civilization represents an incredibly brief phenomenon, lasting mere tens of thousands of years compared to the billion-year timescales characterizing galactic evolution, stellar life cycles, and the grand recycling processes that connect our biological existence to cosmic chemical cycles operating throughout the observable universe. Our species occupies a unique position as conscious observers capable of recognizing our participation within these vast systems, understanding our cosmic origins through scientific investigation, and appreciating the profound interconnections linking terrestrial life to stellar evolution, galactic dynamics, and universal structure formation processes that created the conditions enabling awareness itself to emerge from cosmic matter arranged in patterns complex enough to contemplate their own origins and place within the evolving architecture of space-time. This perspective transforms humanity from isolated inhabitants of a single planetary surface to cosmic citizens participating in universal evolution, connected through physical processes and chemical law. Heritage to stellar systems throughout Andromeda, the Milky Way, and countless other galactic communities distributed across billions of light-years of space that share common origins, evolutionary principles, and ultimate destinations within the continuing story of cosmic development. What new chapters in Andromeda's cosmic story await revelation as humanity's most sophisticated astronomical instruments prepare to peer deeper into galactic mysteries than ever before possible? The James Webb Space Telescope, with its unprecedented infrared vision capable of penetrating cosmic dust clouds that obscure visible light observations, promises to unveil hidden star formation regions within Andromeda's spiral arms, while revealing the faintest stellar populations scattered throughout its extended halo system. Webb's extraordinary sensitivity enables detection of individual red giant stars at Andromeda's distance, potentially doubling or tripling the census of resolved stellar sources available for detailed kinematic and chemical analysis that will refine our understanding of galactic structure, evolution, and the merger processes that shaped its current architecture. The telescope's ability to observe in multiple infrared wavelengths simultaneously provides crucial advantages for studying stellar populations of different ages and metallicities, distinguishing between indigenous stars formed within Andromeda itself and immigrant populations accreted from disrupted satellite galaxies during ancient merger events that left permanent fingerprints within contemporary stellar distributions. Meanwhile, the Nancy Grace Roman Space Telescope's revolutionary wide-field capabilities will transform dark matter research through comprehensive mapping of stellar streams, gravitational microlensing surveys, and systematic searches for the subtle perturbations that reveal invisible subhalo populations embedded within galactic dark matter distributions across unprecedented spatial scales. Roman's coronagraphic instruments may even achieve direct imaging of massive exoplanets orbiting stars within Andromeda's nearest regions, potentially providing the first glimpses of worlds existing within our neighbouring galactic system, and expanding the search for potentially habitable environments beyond our local stellar neighbourhood. Despite these advancing technological capabilities, fundamental questions about Andromeda's nature remain tantalizingly unanswered, beginning with the ultimate identity of dark matter itself, and whether the apparent deficit observed within Andromeda's halo represents genuine mass shortage or systematic errors in theoretical predictions about how galaxies should acquire and retain their invisible gravitational scaffolding. The precise timing and sequence of merger events that created Andromeda's complex stellar population mixture requires further investigation through improved stellar dating techniques, enhanced chemical abundance measurements, and sophisticated computer simulations capable of reproducing the detailed observational signatures preserved within contemporary galactic architecture. Formation details governing how primordial gas clouds collapsed into the first stellar generations, assembled into galactic building blocks, and eventually merged to create systems like Andromeda remain poorly understood despite decades of theoretical development and observational progress toward understanding cosmic structure formation processes operating since the earliest epochs following universal recombination. The technological horizon extends beyond currently planned missions toward revolutionary concepts, including space-based interferometry networks spanning enormous baselines, quantum sensors capable of detecting gravitational wave signals from galactic-scale events, and artificial intelligence systems sophisticated enough to identify subtle patterns within astronomical datasets that exceed human analytical capabilities. Next-generation extremely large ground-based telescopes with collecting areas measured in hundreds of square meters will achieve sufficient light-gathering power to conduct spectroscopic surveys of individual stars throughout the local group, potentially enabling detailed chemical analysis of stellar populations within dwarf galaxies, stellar sun streams, and other faint structures that preserve archaeological records of cosmic evolution across billions of years. Advanced space missions utilizing formation-flying telescopes, gravitational wave detectors, optimized for galactic frequency signals, and precision astrometry satellites capable of measuring stellar motions with micro-arc-second accuracy will gradually resolve current uncertainties about galactic dynamics, dark matter physics, and the fundamental processes governing cosmic structure formation throughout the observable universe. The patient nature of scientific discovery ensures that these revelations will emerge gradually through decades of careful observation, meticulous data analysis, and the slow accumulation of evidence that eventually crystallizes into revolutionary insights about cosmic architecture and evolution. Astronomy operates on timescales that span human generations, with major discoveries often requiring decades of preparatory work, technological development, and observational campaigns before yielding definitive answers to fundamental questions about universal structure and the physical laws governing cosmic evolution. This measured pace reflects both the enormous scales involved in astronomical phenomena and the careful methodology required to distinguish genuine discoveries from instrumental artifacts, measurement uncertainties, and theoretical biases that can mislead scientific interpretation despite the best intentions and most sophisticated analytical techniques available to contemporary researchers. The continuing story of Andromeda's exploration exemplifies how science advances through patient accumulation of knowledge, with each observation adding incremental understanding that gradually builds toward comprehensive theories capable of explaining cosmic phenomena across the full range of scales from stellar evolution to universal expansion. How does our nearest galactic neighbour serve as both cosmic lighthouse and celestial mirror, guiding our understanding of galaxy evolution while reflecting truths about our own stellar home that remain forever hidden from internal observation? Andromeda functions as astronomy's most valuable beacon for comprehending the fundamental processes that govern spiral galaxy development, stellar population evolution, and the complex interplay between visible matter, dark matter, and cosmic structure formation operating throughout the observable universe. This magnificent stellar city broadcasts detailed information about galactic physics across 2.5 million light-years of intergalactic space, carrying within its starlight the encoded secrets of how massive galaxies assemble their components, regulate star formation activity, and respond to gravitational perturbations from neighbouring systems throughout billions of years of cosmic evolution. Every photon arriving from Andromeda's spiral arms, stellar halo, and satellite galaxies delivers crucial data about stellar nucleosynthesis, chemical enrichment cycles, dynamical heating processes, and the hierarchical merger events that transform simple gaseous building blocks into the architecturally sophisticated galactic ecosystems we observe throughout the contemporary cosmos. The lighthouse analogy captures Andromeda's essential role in illuminating cosmic processes that operate on scales far too vast for laboratory reproduction, providing the only accessible natural laboratory where astronomers can study galaxy formation physics in complete detail across spatial dimensions, spanning hundreds of thousands of light-years and temporal intervals encompassing the entire history of stellar evolution since cosmic dawn. As a celestial mirror reflecting the properties and evolutionary pathways characteristic of spiral galaxies throughout the universe, Andromeda enables astronomers to understand their own galactic home through external perspective that remains impossible to achieve from within the Milky Way's stellar disk, dust lanes and spiral arm structures that block comprehensive views of our galaxy's overall architecture and large-scale organization. The mirror relationship works both directions, with Milky Way observations providing complementary insights about stellar populations, chemical abundance patterns, and kinematic structures that can be compared with Andromeda's properties to identify universal principles governing spiral galaxy physics versus unique characteristics reflecting different formation histories, environmental influences, and stochastic merger sequences. This comparative approach reveals how individual galaxies represent unique solutions to the cosmic structure formation problem, with each system developing distinctive stellar population mixtures, morphological features, and dynamical properties through complex interactions between deterministic physical laws and random gravitational encounters that create the remarkable diversity observed throughout galactic surveys spanning billions of light-years. Our local group galaxy cluster functions as nature's most accessible laboratory for studying cosmic evolution processes under controlled conditions where individual stellar sources can be resolved, chemical abundances can be measured precisely, and gravitational interactions can be monitored across human observational timescales that span multiple decades of continuous astronomical investigation. This cosmic laboratory contains examples of virtually every type of galactic system known to exist throughout the universe, from massive spiral galaxies like Andromeda and the Milky Way to intermediate mass systems like triangulum, dwarf ellipticals, irregular galaxies, and ultra-faint stellar associations that preserve fossil records of the earliest epochs of cosmic structure formation, when the first generation of stars began transforming primordial hydrogen and helium into the heavy elements necessary for planetary formation and biological complexity. The experimental advantages of local group proximity enable detailed studies impossible to conduct with more distant galactic systems, where entire stellar populations remain unresolved, and subtle phenomena like stellar streams, chemical gradients, and kinematic substructures disappear below observational detection thresholds despite their crucial importance for understanding galactic assembly processes and dark matter physics operating throughout cosmic history. Perhaps most profoundly, the connection across space established through electromagnetic radiation creates direct physical links between human consciousness and stellar processes operating within Andromeda's vast gravitational territory, binding our awareness to cosmic phenomena through photons that began their journey when early human ancestors first developed tool-making capabilities and cooperative social structures. This luminous bridge spanning intergalactic distances transforms astronomical observation from passive data collection into active participation within cosmic information networks that connect conscious observers to stellar evolution, galactic dynamics, and universal structure formation processes operating across spatial scales that encompass the largest gravitationally bound systems in the observable cosmos. The ancient starlight reaching Earth tonight carries within its spectral signatures the accumulated wisdom of stellar nucleosynthesis, supernova explosions, and cosmic chemical evolution that enabled the emergence of complexity, consciousness, and scientific understanding capable of recognizing these profound connections linking terrestrial life to galactic processes distributed throughout the expanding space-time framework governing universal evolution since the cosmic microwave background radiation last scattered during the recombination epoch approximately 380,000 years after the Big Bang initiated cosmic expansion and structure formation. What profound mysteries await discovery within the ancient photons arriving tonight after their 2.5 million year journey through cosmic darkness, carrying encoded messages about stellar births, galactic collisions, and evolutionary processes that continue reshaping Andromeda even as we observe its distant brilliance. Each particle of light reaching Earth tonight began its voyage when our planet's ice ages were carving continental landscapes, when primitive human ancestors were developing the earliest stone tools, and when biological evolution was still millions of years away from producing the cognitive capabilities necessary to contemplate cosmic distances and galactic architecture spanning the vast scales we now recognize through astronomical investigation. These photons witnessed the entire span of human evolution from its earliest origins through the development of agriculture, civilization, technology, and ultimately the scientific revolution that enables contemporary observers to decode their spectral messages about stellar temperatures, chemical compositions, kinematic motions, and the gravitational processes governing galactic dynamics across cosmic timescales. Every star visible within Andromeda's magnificent spiral arms serves as a stellar time capsule preserving specific moments in cosmic history, with massive blue giants documenting recent episodes of star formation triggered by gravitational interactions, yellow dwarf stars like our Sun recording intermediate periods of galactic chemical enrichment, and ancient red giants maintaining memories of primordial stellar generations that formed when the universe contained only hydrogen, helium, and trace quantities of lithium produced during Big Bang nucleosynthesis. The temporal stratification encoded within Andromeda's stellar populations creates a comprehensive archive of the galactic evolution spanning nearly the entire 13.8 billion year history of cosmic structure formation, with different stellar types serving as chronometers that enable astronomers to reconstruct the sequence of merger events, star formation episodes, and chemical enrichment processes that transformed simple primordial gas clouds into the architecturally sophisticated galactic ecosystem we observe today. Far from representing a static astronomical object frozen in unchanging configuration, Andromeda continues evolving through ongoing processes that operate across human observational timescales, including active star formation within molecular cloud complexes, stellar evolution through nuclear burning phases that alter surface temperatures and luminosities, gravitational interactions with satellite galaxies that trigger tidal disruption and stellar stream formation, and the slow orbital decay of binary star systems that occasionally culminate in spectacular nova explosions visible across intergalactic distances. Advanced astronomical monitoring campaigns have already detected subtle changes within Andromeda's structure during the past few decades of systematic observation, including the discovery of new variable stars, the brightening and fading of stellar sources undergoing evolutionary transitions, and the gradual motion of stellar streams and satellite galaxies responding to complex gravitational forces operating within the local group's dynamical environment. These contemporary transformations remind us that cosmic evolution continues operating at immeasurable rates even within systems so distant that their light requires millions of years to traverse the intervening space, demonstrating that the universe remains dynamically active across all observable scales from planetary motions through stellar life cycles to galactic interactions and cosmic expansion itself. Future generations of astronomers will undoubtedly discover phenomena within Andromeda that current technology cannot detect, revealing new layers of complexity within galactic structure, unexpected connections between stellar evolution and cosmic chemistry, and perhaps entirely novel physical processes operating under extreme conditions that cannot be reproduced within terrestrial laboratories or anticipated through contemporary theoretical frameworks. The invitation to continue looking upward and wondering about cosmic mysteries represents more than mere intellectual curiosity. It acknowledges humanity's fundamental connection to cosmic processes that created the elements composing our bodies, the energy powering our metabolism, and the physical laws governing everything from atomic interactions to gravitational dynamics operating across the largest scales accessible to scientific investigation. Each moment spent contemplating Andromeda's distant majesty reinforces our participation within cosmic evolution as conscious observers capable of recognizing beauty, understanding complexity, and appreciating the profound interconnections linking terrestrial life to stellar processes distributed throughout galactic systems, separated by the distances that challenge human comprehension yet remain accessible through electromagnetic radiation that carries information across cosmic gulfs spanning millions of years of travel time. The wonder awakened by astronomical observation extends beyond scientific knowledge toward deeper appreciation of our cosmic heritage, our temporary existence within an evolving universe, and the remarkable privilege of conscious awareness emerging from matter organized into patterns sophisticated enough to contemplate their origins, recognize their connections to distant stellar cities, and experience awe at the magnificent scales and intricate beauty characterizing the cosmic umgis, architecture surrounding our small planetary home within the vast expanding space-time framework that encompasses everything we can observe or imagine.